I'm Cody Root. This is the Church of Logic, and we're now at our part 4 of linear logic with Chris Martens and Rob Simmons. Brainstorm that offline. Okay, so let's get back to pattern matching, because I think this is cool, and I feel like I read this paper, by someone called Noam Zylberger, and it felt very inspiring. Let's see. Somehow I felt like, this pattern match things versus call a function on things.
Mm-hmm.
It had this very deep sort of consumer versus producer duality.
Right.
And somehow that this was related to linear logic. And I don't know. This is an unformed thought, but can you try and evoke those ideas?
Yeah, so I mean, this might be a good time to bring up the word polarity, which can sound a little intimidating. It sounds very science fictional, reverse the polarity or whatever. But this idea of polarity is sort of like you can characterize the types as being what we call positive or negative, and what Cody was alluding to of like the sorts of types you can inspect through, whose values you can inspect through pattern matching are the positive ones, right? They have structure to them that you can take apart and inspect. They're made out of data in combination, and then the things that you can really only inspect or interact with as like black boxes by poking them, whether that's like a function that you're calling or a some kind of machine that's going to give you like a the with connective, right, is like you can kind of poke it and you can get out, you can send it a message saying I would like an A or I would like a B,
I see.
And then it kind of sends that back to you, but you don't get to inspect kind of what its structure is.
I see. And you're saying that these different connectives, these two ands in some sense, their difference is that they have a different polarity, and that's going to dictate essentially what programming constructs are going to correspond to those types in the the propositions as types.
Yeah, exactly. And it was linear logic kind of forcing us to actually write down these forcing us to elucidate these points of variation where we could describe different connectives in these different ways that gave rise to acknowledging even that polarity is a thing. And then we realized in retrospect, like, oh, hey, we can actually apply this in settings that aren't just linear logic or aren't just a linear type system. They still matter to programming.
Okay, I think that's really cool, but I also want to know, hey, what does that give us? Like, how is this exciting for like, hey, here's a real like application here. And I actually think I have one in mind because I saw Zena Ariola talk about, now I wish I'd prepared this. She talked about, hey, if we have this natural view of these different kinds of connectives, it naturally helps us, I'm blanking. I remember being enlightened when I saw the talk. What does it naturally help us do?
Well, so an answer, and this may, while you're thinking about that, an answer, and something that did actually kind of show up in parallel as a discovery of the ideas of polarity that wasn't in linear logic, and then we kind of realized that these ideas converged, was what was called call by push value, which was this other discovery from a more programming perspective instead of a more linear logic perspective of kind of what's going on with this distinction between the positive things, the data, and the negative things, the computation. And the thing you got out of that was a single language that gave a clear type-based understanding of what call by name versus call by value, these two like Haskell-y and ML-y strategies were, because in the viewpoint here is that in an ML style language, call by value is the argument to a function as a value. We're treating it as positive, so we need to evaluate it all the way down to its data and then pass it to the function. Whereas you can kind of look at the Haskell lazy thing as saying when I'm passing an argument to a function, I'm not expecting that to be a thing that's valued. I expect that to be more negative because it's a thing that I might poke later and ask what it is.
Yes.
And so that,
with some subtleties there.
With a lot of subtleties, right? And so that this is the and
yeah. But in this quest for some kind of unifying framework to talk about both call by name and call by value stuff, like they came across this same idea.
And this is useful. Okay, so I still don't remember what
Zena's talk was about.
What Zena's
Did it have to do with co-induction? Because she talks about
yes, it had to do with co-induction.
Okay.
Okay, I do remember in Noam's paper, he says, hey, you know what's hard? Having a type-safe functional language with references. It's actually really easy to screw that up. You just have mutable references. I think he also talks about union types, though I was a little disappointed because he motivates his whole paper with union types, and he just doesn't talk about it. But anyway, union types, mutable references, all this is subtle. It's really easy to write a language that's just broken.
Yeah.
And people do that, right? I think the original Camel was not type safe because they didn't get polymorphism and reference types correctly.
Yeah.
The original standard ML was too. They like the original definition of standard ML had a problem, and Derek was like, the compiler is broken. This was Derek Driver. I think the in this story.
So one thing that I think I came about to the long way was respect this linear logic and polarity kind of concept as, these are all like programming concepts we already kind of know and we know how to implement, but hey, if you have these concepts present in your mind, it's a lot easier to know when you're building something that's not going to work, or you're in dangerous ground, right? If you're using a positive polarity thing in a negative, position, well, some alarm should go off, and usually when that alarm goes off, it means either you're in dangerous ground or you've already committed a sin and your language is not type safe. And so, despite not bringing some crazy new paradigm, I guess it sort of does bring a crazy new paradigm, but despite not, being like quantum computing and like some completely out of the blue new computational operation, it does give you a lot because it tells you, hey, when I design my language, here are guardrails that make it harder to screw up. And let's talk about co-induction very briefly.
Oh boy.
This is kind of, let's see, I haven't even been keeping track of time, so I feel bad. Maybe this is, we should start kind of wrapping it up. But,
sure.
But let's talk about co-induction.
Okay.
Let's see, maybe I can start. So it's pretty natural to want to write terminating programs. One way to do that, let's see, it's hard to write terminating programs, but one way to kind of do that is make sure something is going down. And one way to make sure something is going down is to take a structured object, and at each kind of loop of computation, you have to destructure that object. And in addition, those structured objects have to be kind of finite, like finite lists or finite trees or something. And if you're destructuring, you're going down in the tree each time or down in the list, and you're going to hit the end at some point. Your loop is going to necessarily terminate. Great. Okay, that's one half of the story. In practice, we write programs that are supposed to run indefinitely all the time, like servers is kind of a classic example. But those things, you don't want them to just be while true loops, right? They're supposed to do something once in a while, right? If a server is just looping, basically it's in DDoS, right? It's not responding. You want it to run forever, but always eventually respond.
Yeah.
There's a lot to say there, but but one way is you want this kind of list analogy. You sort of want to say, hey, in a loop, if every time I have a finite list, I'm moving forward in the list, I'm destructuring the list, eventually I'm going to terminate. We kind of want an analogy of, hey, if this thing happens each time, then maybe I'm going to run forever, but each time I'm going to be like responding to requests.
Yep.
All right, that's my introduction. That's all I got. You want to tell me what this has to do with linear logic?
I actually have no idea.
Well, so I think that there is this natural sense in which the positive data types end up
Oh, sure, with polarity, yeah.
it end up being very connected to data, to, again, like this is the, I've got to like compute this all the way down to stuff.
Let's talk more concretely, right? Like
Right.
the typical example of like an inductive data structure is a list, right?
Yeah.
You write an inductive function over a list, like it's going to destruct as long as you're destructing and only making recursive calls on the pieces.
Yeah.
Like you'll get to a base case eventually. By analogy, the sort of typical co-inductive data structure is a stream, which is can be characterized as, some people would call this like a lazy list. Something where like you can get some data out of it, but then the rest of it is going to be a stream, but then that never actually has a base case. There's no nil case in the description.
So right. So here we see the analogy a little bit, right? We see that this pattern matching, this let x, y equals pair, that feels like an inductive data type, right? You're matching against it, you're destructuring it. And then this, get the head of the stream, or get the next token returned by the stream. That feels a lot more positive, I guess?
Or negative.
Negative?
Yeah.
Yeah,
Okay.
the poke, because when you're saying get the next thing, you're poking the stream, right? That's the negative bit.
Yes.
You're sending, so message passing is fundamentally what is happening with negative bits. When you're taking a stream and you're like, give me the next thing, then
You're sending in a message.
You're sending in a message. Now, in order to have an interpretable thing that you get back, that's got to be positive. So you've got to poke the stream,
Right.
which
like
is
the data is going to be positive, but then it also still gives you back a thing which you can continue to poke.
And that would be
the rest,
also a stream. The rest of the stream.
multiplicative and...
that'd be exactly.
So the type.
Right. It's like a positive thing tensor a negative thing.
Yeah.
Okay, so positive and you get both, but one of the things is a negative. You only get to poke it.
Mm-hmm.
Great. All right. Well, this is very cool. I don't know if I have personally much more bandwidth to understand all these things, but it's fun. Is there some last remark you want to make? Takes less than a minute or two.
I guess like one more thing just to follow up on this idea of like positive and negative data in programming. One of the things that's really interesting to me is the way you can kind of characterize, like just in the same way that we could characterize pairs through these two different kinds of conjunction, we can also actually have we can have an account of something that looks sort of like an object-oriented view of things, but from within a more standard functional setting, by thinking of objects as essentially the negative data types, the things that we can basically, calling a method corresponds to like sending a message to this negative thing, and passing it in some positive data and then getting some data out, but then like recursively getting back the thing that's negative that you can still continue to probe.
Cool. Yes. Yeah. I guess I'm probably not gonna do an episode on small talk.
No, I mean,
this is
sure.
a programming blog, but
now you don't need to, because I think that you can look at.
You can give a logical account of these things that are standard programming idioms in other places, and I think that's neat.
Yeah, that is neat.
Yeah.
All right, Rob.
Yeah, and I do think that there's this way in which you can say, okay, it's really easy to identify the ways in which Java has failings because it does not account for positive data type. It doesn't have object destructuring, or at least it didn't when I was last paying attention a while ago. And you can also identify ways in which functional languages could have better support for these kinds of negative and message passing ways of looking at things. And so I do think that, and again, it moves away from logic, but as Chris was suggesting, this is a thing that's valuable to have an understanding from when you're starting to think about the foundation of a next generation of programming languages.
Great. That's a very good tie the bow on it. So thank you both, and I hope you'll both come back. We'll see how it works out. And everybody out there listening, take care. Until next time.
Bye.
Do you have a standard sign off that you use?
That
to
was
see
it.
you next time. Okay, that's